Hi everyone. In today's video, we will be covering our Chapter 5 material, which revolves around the idea of the normal distribution. To jumpstart into our conversation about the normal distribution, we first have to define what it actually is. And in this case, it is a type of continuous probability distribution for a random variable. A normal distribution is represented by a symmetric bell-shaped curve in which the distribution mean, median, and mode are the exact same value. So think back to our previous lecture and chapter material about measures of central tendency. We talked about how skew can come into play when the mean, median values can be different, either larger or greater than one another, and how that can result in either a positive or a negative skew on our distribution. The last type of distribution shape that we had talked about, though, was this idea of a symmetric distribution. So that's where it's exactly equal on each side, and that's what's being represented here in this cartoon. It's this bell-shaped curve, again, where that mean, median, and mode are all in that center point here. Importantly, the normal distribution is a theoretical model, although some really large data sets approximate this. So one common example we often cite is height distribution within the adult population. In this case, we have a mean, median, and mode value that tends to end up being the same. And so our distribution, in this case on our x-axis, would be something like height in inches. And eventually we would see a type of distribution that would mirror a normal distribution, in which sometimes we have extreme examples where people are very, very short, and they would end up here on the left end of our distribution. And we also have examples too where people are extremely tall, and they would end up on the right-hand side of our extreme values in distribution. But we know that most folks actually are somewhere here in the middle. So if we were to get enough individuals to take a sample and to emulate the entire population of a country or a state even, it would eventually end up looking like a normal distribution. But keep in mind here that overall, the normal distribution is a theoretical model. We use this exclusively with large samples in populations, so this is not something you would be seeing with a small descriptive sample, like a class size or anything like that. Importantly, too, the normal distribution tells us the percentage or the proportion of data within 1, 2, 3, even 4, so on and so forth, standard deviations from the mean. And so this is bringing in together the information that we've learned so far in chapters 1 through 4 in terms of measures of central tendency and our measures of variability, specifically with calculating this idea of the standard deviation and how we can actually approximate those values relative to really large data sets and distributions. So what we're looking at here is the theoretical model of the normal curve. And so our anchoring statistics in this case are our measures of central tendency, which are our mean, median, and mode. And those will be always at the center of our normal curve and distribution. I know we learned how to calculate a standard deviation in chapter 4, but just as a brief reminder of what that actually is measuring is the spread of the data within our distribution. And so the further away you get from our mean values, whether that's in a positive or a negative direction, the further away or the less likely those odds are to occur relative to what your mean, median, and mode values are. Before we dive into the rest of our conversation regarding the normal curve and distribution and how we're going to use this to calculate various forms of statistics, I want to take a step back for just a moment and explain why the normal curve is important in social science. And there's 4 key reasons, and we'll go through each of these in detail. The first is that the normal curve models many social phenomenon, things such as height, income, IQ scores, test scores, certain attitudes. So a lot of times like political affiliations and attitudes towards certain social issues end up being on a normal curve and things of that nature. And because of that, it already roughly approximates a normal distribution. And so it's not that much of a step for us to move from that actual real world model to our theoretical model of the normal distribution. Secondly, the normal curve underpins statistical inference. And what do I mean by that? A lot of social science research relies on statistical tests, such as t-tests, which is something we'll learn about in later chapters, ANOVA, and regression. And that data are all assumed to be normally distributed. And because of that, that allows researchers to estimate things such as probabilities, which we will also cover in a later chapter, calculate things such as confidence intervals, which we'll do in chapter 7, and make inferences from a sample to a larger population. Third is this concept of the central limit theorem, which is also known as CLT. And this is what tells us that regardless of what the shape is of an underlying data set, the sampling distribution of the sample mean will approximate a normal distribution if the sample size is large enough. So oftentimes in social science, any type of sample that's over 30 in nature is considered normally distributed. And as we increase our sample size, we more so and more so approximate what a normal curve and distribution would be in our theoretical model. And lastly, the normal curve allows us to evaluate individual observations. This is through something called z-scores, which is what we'll be calculating at the end of today's lecture. With z-scores and through those calculations, we are able to standardize different types of data and compare how individual scores relate to a broader population. We'll get to a couple examples of those later on in this lecture, but overall, just keep in mind why we're doing this in the first place. It's because it allows us to make inferences, and now we're moving into our conversation away from descriptive statistics, which is what we had in the first couple chapters, to more so making inferences about our data from moving from smaller samples to larger populations, and even from individual data points to be able to see where do we fall within the concept of the normal curve and a normal distribution as well. With all of that in mind, let's take a look at a real-life example of how we might use the normal distribution within social science and science research. In this case, what we're looking at here is a distribution of summer temperatures in the Northern Hemisphere between the years 1951 and 1980. And so what we see in this middle section here, which is what we would suppose is both our mean, median, and mode values, is what's considered a normal temperature in a summer time period. We can see that using these years and varied temperatures, we're beginning to see the development of a normal and bell-like shaped curve. And because of that, we can use things like the normal distribution to calculate how individual data points may differ from what's considered normal. So in this case, what science researchers, and particularly climate scientists, could do is take examples of certain summer temperatures that they're receiving within a northern hemisphere region and see how that relates relative to all of the other summers that they have recorded here. So let's say, for example, in the year 2020, they found that the average summer temperature was all the way here on this extreme end of our distribution. What they're able to do is not only take that singular year if they'd like to. So in this case, let's say they wanted to take 2020 and they were just trying to see how hot is this relative to all the other years that we have on record here. What you can also do is not only evaluate that individual data point through something like a z-score, which is what we'll be getting to soon. But what they can also do is, after plotting these out, is let's say we had a number of years as of late in which all of our summer temperatures were being recorded in this extremely hot area here. What they're able to do using the normal curve in statistics is see what is the probability that we are actually way beyond what is considered normal for this. How many standard deviations are we above the mean relative to what we would expect at certain times of years? And so that's what the normal distribution and z-scores and different types of statistics allow scientists to do. And so they can predict patterns and extrapolate up different types of scientific inquiry just based on this theoretical model. Let's take a look at a slightly less abstract example. In this case, this is my actual Wordle distribution. And if you're unfamiliar with what this game is, it is through the New York Times, and it's basically just a basic word game in which you have 6 opportunities every day to guess a 5-letter word. Within those 5-letter words, they will turn certain letters green and yellow to indicate to you whether the position of the letter is correct. And so that is kind of a guide to tell you what the Wordle or the word of the day is. And so what we're taking a look at in terms of this graphic here is my distribution in terms of my guesses. So how much on average does it take me to guess what the Wordle is? In this case, eventually, even though we're using a smaller sample size here, only 882 cases, theoretically, if I were to keep playing this game over and over and over again, I would eventually achieve a normal-like curve, which is what you see starting to form here. But something to ask yourself in the context of this is this question here. If this distribution was perfectly normal, meaning it's that bell-like shaped curve that we saw in the previous slides in our theoretical model, what would the mean, median, and mode be of my distribution? So take a moment here, go ahead and pause the video and take a look at the graphic. I'll let you do that and then we'll come back and discuss what that answer would be. Okay, hopefully you've taken a second to pause the video and take a look at that. And in this case, if this was a perfectly normal distribution, again, that it would mirror the perfect bell-shaped curve over here on the end, my mean, median, and mode value would be 4. In other words, on average, it takes me 4 guesses per day to get the Wordle correct. So, not that that's a perfect emulation of this here, but if I kept doing this more so and more so, I would start seeing more of this bell-shaped curve evolve over the time I keep increasing my sample size. So now that we've taken a look at a couple real-world examples of how we might use the normal curve to calculate statistics, let's briefly talk about this concept called the empirical rule. You may also see this designated as the 68, 95, 99 rule. Just know that those two terms are interchangeable. And so, this empirical rule falls under the idea of the normal distribution itself. And what it supposes is that with an approximately normal distribution, approximately 68% of data, so all of our observations, are going to lie within 1 standard deviation of the mean, which is what you see here. Approximately 2 standard deviations are going to contain 95% of our observations. And lastly, nearly all of our observations, or upwards of 99%, will fall within 3 standard deviations of the mean. Let's take another look at how we can visualize this. In this shaded region here, what you're looking at is the area of data points that would fall within 1 standard deviation of the mean. And so again, that's 68% in this theoretical model. This second shaded region is what we would suppose 2 standard deviations worth of observations would fall under, and that's approximately 95%. And lastly, within 3 standard deviations of the mean, we would expect almost all of our observations to fall within this. However, there is room on either side of the distribution, both in the negative and positive realms, for observations that might fall outside of 3 standard deviations of the mean. So even though we get upwards of 99% that are contained within it, we still have approximately 0.28% or 0.14 on each side of our distribution that could be either above 3 standard deviations of the mean or below 3 standard deviations of the mean. So let's use this rule in an illustrative example. And in this case, we'll take a look at the number of hours men sleep per night. Next, we're going to look at a distribution that illustrates the number of hours women sleep per night. And so in this case, what we would suppose with an average number of hours per sleep, so remember that our Y bar is showing our average here, is 7 hours. And we're also supposing that it is a standard deviation of 1, or 1 hour in this case. So using the empirical rule, we can calculate the percentage of men within the US adult population that would sleep between certain hours of time. In this case, we would suspect that approximately 68.26% of men sleep between 6 and 8 hours per night. Reason being, again, we have our mean value of 7 here, and then 1 standard deviation is 1 hour. And again, I'm just getting that from our information here. So 1 hour below and 1 hour above our mean. So I'm doing a +1 and a -1 here, which is what you see in my calculations here off to the left. Secondly, we would suspect that approximately 95% of men would sleep between 5 and 9 hours of sleep per night. Again, that's within 2 standard deviations of the mean. And lastly, we would expect approximately 99.72% of men to sleep between 4 and 10 hours per night. So the vast majority of men are going to sleep within this range, but there might be folks who can actually get away with sleeping less than 4 hours. It's not very common, and within our theoretical model, it would only be approximately 0.14% of the population. So it's not impossible, but it's improbable. Same goes for above our standard deviation of 3 in this case. We would suspect that approximately 1 or 0.14% of the population needs to sleep an average of above 10 hours of night for men. So again, it's not impossible, but it's not very likely that any observation in this case would fall below 3 standard deviations of the mean or above 3 standard deviations of the mean. Let's take another look at an example in which we are approximating the number of hours of sleep required by women on average. And in this case, notice that the standard deviation has changed. For women, their spread is smaller, meaning that they have less variability in terms of how many hours of sleep they are having each night. So in this case, within 1 standard deviation of the mean, which is where 68.26% of our observations for our female population would lie, we would expect them to sleep between 6.5 and 7.5 hours per night. Again, my standard deviation has changed here. And so instead of a value of 1, in which we saw with our male population having that greater spread, for females, it's less, meaning that more of them are falling within a concentrated range, and we'll get to this in just a second down here. We would suspect that approximately 95.44% would get between 6 and 8 hours per night. And lastly, the majority of our distribution, or in this case, 99.72% of our observations, sleep between 5.5 and 8.5 hours per night. Again, this is just approximating those values, and there are individuals that could end up on this type of distribution in which they are below 3 standard deviations, so less than 5.5 hours per night, and some that are going to be above 8.5 hours per night. And so it's not probable that you'd end up on either end of that distribution, but it is a possibility. So far within this lecture video, we have used the normal distribution to calculate the percentage of our data that might fall within 1, 2, and 3 standard deviations of the mean. We did this by using our empirical rule, which is also that 68, 95, and 99 concept we talked about a few slides ago. But we can also apply this same knowledge and distribution to understand where one single observation lies relative to the rest of the data within our distribution. That's where this idea of z-scores comes in. And a z-score is the distance between an observation and the population mean in units of a standard deviation. And so this makes it possible for us to directly compare observations even across different scales and units. And so that's where this concept of a standardized score comes in. And so you can kind of think of a z-score as a number of standard deviations away from the mean, but with a direction. And so once we calculate a z-score, it will tell us whether or not we are above the mean or below the mean, because we'll be able to see if that z-score calculation comes out to be a positive or a negative number. When a normal distribution is represented in z-scores, we call that the standard normal distribution. And so that's kind of bringing together all of the concepts that we've talked about thus far. And let's talk about how we would actually calculate these. And here is the formula to calculate a z-score. And as a reminder, that z-score is the distance between an observation and the population mean in units of the standard deviation. So again, it's going to tell us how far above or below the mean we are. In this case, z is what we're calculating for. We're going to start by figuring out what that individual data point is, which is represented by y. So that is our individual observation here. Next, we will have to know what our mean value is, or y bar. We take our original observation and subtract that from our distribution mean, and lastly, divide that by our standard deviation. The result of that calculation will give us our ultimate z-score. So let's practice calculating using z-scores how bad or good the St. Louis Cardinals are in terms of RBIs compared to all of the other teams, and we'll do this for runs allowed as well. So let's calculate two examples here using the normal distribution for the St. Louis Cardinals in terms of runs batted in, or this concept of RBIs, and also runs allowed. And so what we're looking at here are two approximately normal distributions. And again, you can see how we're starting to get a bell-shaped curve in both of our distributions here. And so we'll be calculating the z-score for both the St. Louis Cardinals RBIs and also runs allowed. If you're not as familiar with baseball, RBIs are the number of runs you bat in per game. So in this case, a higher score is better, so you want to be above the mean or above average. In contrast, in terms of runs allowed, that's how many runs you're giving up a game, and so you want to have less runs allowed, so lower is better in this case. I've already done the heavy lifting for us in terms of calculating what our mean standard deviation is, and then this is our individual observation. So how many RBIs did the St. Louis Cardinals have? They had 685 in this season. And what you're looking at in terms of the distribution here is all of the other teams within Major League Baseball. And so our y-axis is showing how many teams scored a certain amount, and our x-axis is showing the number of RBIs per team. Similarly, on our right-hand side distribution, our y-axis is showing us the number of teams, and our x-axis is showing us runs allowed. So let's first take a look at our distribution in terms of runs batted in, or RBIs. Again, a higher score is better, so we want to be above average and above the mean in this case. All we're going to do in this particular example is use the information that I had provided in terms of our mean, standard deviation, and the number of RBIs the St. Louis Cardinals had in this season to see where they were with respect to all of the other teams within Major League Baseball. And so what I did here was take our z-score formula, which again, y represents our individual observation, which in this case, in that particular season, the Cardinals had hit in a total of 685 RBIs. We're going to subtract that by the average, or how much on average did Major League Baseball teams have in terms of RBIs. So that is league-wide, not just among the Cardinals. And lastly, we're going to divide that by our standard deviation, which in this case is 68.219. And so once I plug in all those numbers, I end up with a z-score of 1.224. In other words, remember that our z-score can be interpreted in terms of how much or how much below we are in terms of our standard deviations above or below the mean. So in this case, the Cardinals are 1.224 standard deviations above the mean, which in this case is a good thing, right? Because RBIs are a good indicator that a team is doing well. And so relative to an average Major League Baseball team, the Cardinals are actually doing pretty good on this measure. They are better than a good chunk of other Major League Baseball teams. And so that's a good indicator in their favor. Let's secondly take a look at this concept of runs allowed. And remember, this is how many runs they're giving up in a whole season, and so a lower number is better. You don't want to be giving up runs against the other team. So in this case, our average for the entire league in that year was 629.067 runs, and so that's where I get my average number here, so Y bar. In this particular season, the Cardinals gave up 584 runs, so that's where I'm getting my individual observation, because again, we're only concerned with the St. Louis Cardinals in this example. So that's my Y, and I'm dividing that by my standard deviation of 82.360, which is where I get my S value here. Once I calculate that all in, I receive a z-score of negative 0.547, which means that the Cardinals are negative 0.547 standard deviations below the mean, which is good because, again, a lower runs allowed is better relative to all these other teams. The previous two examples that we just went over in terms of RBIs and runs allowed illustrated an example in which we took a look at one individual observation, or in this case, one team, being the St. Louis Cardinals, in comparison to an entire population, or all of the teams within Major League Baseball. However, we can also use z-scores to help us standardize scores in which the scales between two different types of variables are not necessarily the same. And a very common example of that is the difference between ACT and SAT scores. And so, as many of you are familiar, because you've probably had to take one or if not both these exams, the ACT and SAT are standardized tests in which you submit a score to a university, and they determine how you do relative to other students, and that's what your score represents. However, the scales for the ACT and SAT are not the same. The SAT is measured on a scale between 400 and 1600, whereas the ACT is measured from a score of 1 to 36. So let's say that you took both of these exams. How should you decide which of your two scores you should submit? Well, a z-score can actually help us determine that because it's going to standardize both of these scales within units of either below or above standard deviations of the mean. And so you'll be able to see relative to the average score on both the ACT and SAT, how did you fare compared to what the average score is? So let's take a look at an example of a student who scored 1,020 on the SAT and 19.6 on the ACT, and they're trying to figure out which score they should submit. Importantly, for both the SAT and ACT, the SAT mean is 1083 with a standard deviation of 194, whereas the mean on the ACT is a score of 20.8 and a standard deviation of 4.8 points. And so we'll keep that in mind as we move forward with our z-score calculations here throughout the rest of this presentation. And so let's first calculate our z-score for the SAT. And so in this case, that particular student, their individual score or their Y value was 1,020. That was their score on the SAT. The average for all test takers taking the SAT in that given year, so the mean or average score, was 1083. So you're taking the individual observation and subtracting it by the average. And then your last step is to divide it by the standard deviation, which I took from the last slide, which was a score of 194 points. So in this case, what I did here was plot what the average score is. So this is the mean right here in the middle. Again, we're working with this normal distribution. So the mean, median, and mode are all going to be that value here. So that's why I have it in the middle. I know that the individual observation score of 1020 is below average, and so I just approximated where to put this bar. Once we calculate all of those numbers into our formula, we get a result of negative 0.325. So in other words, we scored 0.325 standard deviations below the mean. And so now we can do that exact same steps using our ACT score. In this case, our test taker scored 19.6 on the ACT, which has an average score of 20.8 with a standard deviation of 4.8. And so when I plug all that information into my z-score formula, I arrive at a final value of negative 0.25. So now that we've calculated the z-scores for both the SAT and the ACT, we can now compare these in terms of standardized units. So in other words, it no longer matters that the SAT is measured on a scale of 400 to 1600, or that the ACT is measured from a score of 1 to 36, because all that we care about now is our mean score and our z-score. I'm going to give you an opportunity here to go ahead and pause this video, and you can compare both of these z-scores to figure out, should we actually be submitting our ACT score or our SAT score? And then we'll have a conversation briefly here in a moment about which one we should do and why. Okay, last chance to pause it if you haven't already, but in this case, we should be submitting our ACT score. And the reason that we should do that is because our z-score in this case is closer to the mean or average score than our SAT score. So in other words, the average score on the ACT was a 20.8. That was our average score on the ACT. And we are only 0.25 standard deviations below that mean score. However, with the SAT, we are 0.325 standard deviations below the mean score of 1083. And so with the ACT, we are closer to the average score than we are for the SAT, and therefore we want to submit what is our higher overall score relative to the mean, and so that's what we should be submitting in this case. I'm going to give you one more opportunity here to practice this on your own. So what I've done here on the left is provided information about another test taker who scored a 1220 on the SAT and a 23.4 on the ACT. And so using this z-score formula provided here, as well as our same information in terms of the mean and standard deviations for both the ACT and SAT, go ahead and pause this video and practice on your own to calculate the z-scores for both the ACT and the SAT. Okay, this is your last chance to pause it if you haven't already, because I'm going to reveal the answers now. You should have calculated a z-score for the SAT of a value of 0.706, whereas the ACT z-score should be 0.542. So you might be asking yourself, similar to our previous example, of which one should I submit? In this case, what's an important distinction between our previous example and this example is that our test taker scored above the mean. They had scores for both the ACT and SAT that were above average relative to all the other test takers that take this. And so in this case, we want to be as far above average as we possibly can. Whereas with our previous test taker who scored both below the mean on both the SAT and ACT, we wanted to be as close to that mean as possible because both those scores were below it. But in this case, we're trying to get to that right side of the distribution and as positive as we can, because the more we are above the mean in terms of standard deviations, the better the score we have overall. And so in this case, we want to submit our SAT score because we are further above in terms of standard deviations above that mean score relative to the ACT. If it's helpful for you to plot it how I did on the previous slide, I highly encourage you to do so. I often do when I'm working through these problems myself in terms of putting that middle ticker for the mean, median, and mode. In this case with z-scores, it will always be that mean. And then you can plot out in terms of the actual observation whether or not you're going to be below or above the mean right away. And so that could be a helpful aspect for you as you're working through these practice problems and also the problem sets that are on your homework as well. Not only are z-scores helpful for us in terms of comparing individual observations to populations or standardizing units across scores such as the SAT and ACT, but it can also help us determine the area under the curve, which we can also really easily convert into proportions, percentages, and percentiles. And because of that, before we jump into this next half of the conversation, I want to reiterate this point that the total area under the curve is 1. So if you recall from chapter 1 in our discussion about proportions, remember that all of proportions have to equal a value of 1. And so the proportion value under this area of the curve is 1. And so anytime we discuss this moving forward, know that all of the areas under the curve will have to equal that value, or you have made a mistake within your calculations. To determine the area under the curve, we actually have a very helpful tool that actually does a lot of these calculations for us. And in this case, it's called the Standard Normal Table. It's also known as Appendix B and is available in your book if you have a hard or online copy of it, or I have posted it to our Canvas page as well under class materials. So let's talk a little bit about what the Standard Normal Table can actually tell us. In this case, once we calculate a z-score, we can go to this first column here and determine what row we want to be referencing here. And in columns B and C, it's going to give us the area between our mean and our calculated z-score value. And it's also going to give us this area C, which is the area beyond our z-score. And so it's essentially doing all of these calculations for us. We just have to take our z-score value and compare it and find it relative to all of this information provided on the Standard Normal Table. So in this case, area B is what you see highlighted here, and area C is that area beyond. I think this will make a little bit more sense in context as we work through a couple examples, so let's get to that next. So what does the standard normal table actually allow us to do? Well, in this case, it helps us interpret z-scores in a way that's a lot more understandable to us than just getting a number such as this. Although z-scores can tell us how many standard deviations we either are above or below the mean, that still might not be the best way for us to interpret that within the context of a problem. What the standard normal table allows us to do, though, is look at both proportions and percentages. So it allows us to interpret these findings in a lot more context than just what the actual z-score says itself. So let's use our previous example about looking at the difference between SAT and ACT scores to illustrate this a little bit better. So let's say you have that SAT score of 1020. Again, remember that the average on the SAT was 1083 with a standard deviation of 194. So that's how we got to this in the first place. We know that you scored below average because not only is your score below the mean, but we also resulted in a negative z-score. So now knowing what the z-score is, we can use this to interpret our results in terms of proportions, percentages, and percentiles. So let's take a look at our standard normal table and how we would actually operate this. So our z-table and standard normal table allows us to look up the associated areas with our z-score on the table itself. And so it rounds all answers to the hundredths place, so make sure, even though we calculated this to the thousands place, that you're rounding accordingly. We are also going to be using what's called the absolute value, so even though our z-score was negative in this case, our standard normal table will only tell us areas in terms of positive numbers. So remember that the absolute value of any number will convert it into a positive number rather than a negative. So in this case, when we round to the hundredths place, we get a z-score of 0.33. Again, we've took the absolute value of that as well, so now we are positive 0.33. And so if I look up that corresponding value on the table, I see that the area between the mean and my particular z-score is 0.1293, and the area beyond z is 0.3707. So let's take a look at what this would actually look like plotted out on the normal curve. As a reminder, our standard normal table is telling us the areas between our mean, so always our middle point here in the normal distribution, relative to our calculated z-score. And so in this case, area B is associated with a proportion value of 0.1293. And again, I got that straight off of the standard normal table itself. And so again, I just did that by taking a look at what the value was for the absolute value of 0.33, which gave me that answer here. The area beyond my z-score was a proportion value of 0.3707. But again, what do these proportions actually mean within context? Well, the area below our z-score, so in this case, area C, is going to tell us the percentage of individuals who scored worse than us on the SAT. So remember that a proportion can easily be converted into a percentage by just multiplying that value by 100. And so that's the only thing we're doing to convert our proportion value of 0.3707 to a percentage value of 37.07. So in other words, we can say that we scored better than 37.07% of test takers. Another way we could phrase that is that 37.07% of test takers did worse than us. So now we can use the information from area C to actually help us calculate our overall percentage about the area above this as well. So let's take a look at that. So on the previous slide, we determined that 37.07% of test takers did worse than us. And that was that area C right here, because remember, this is where our score of 1020 is coming into play. And so there's a couple of different ways we can go about figuring out the percentage of test takers that did better than us. The math on this is going to be the same and give us the same result, so I'm going to show you a variety of methods here, and whichever one works best for you, feel free to use, as long as you show your work. Keep that in mind. Because the area under the curve is always going to equal 1, we know that half of our observations in any given distribution are going to be above our mean value and half are going to be below the mean value. So that's where I'm getting this proportion value of 0.5 listed here. But I also know that there are some test takers that scored better than me, but are still below average, and those are going to be the folks that are in area B right here. Our standard normal table actually gave us this value, so there weren't any additional calculations that we needed to do. In this case, it was 0.1293. So another way for us to interpret this is that 12.93% of test takers did better than us, but were still below average. What I can then do is take that proportion value and add it to this other half of the positive distribution. So what this is showing is all those individuals that did better than average on the SAT. So everyone that scored above this average score of 1083 are now being converted into this proportion value of 0.5. So if I add together the individuals that scored better than me, but not above average, and all the other people that did above average, I get a total of 0.6293. And so a way for me to interpret this is that 62.93% of test takers did better than me on the SAT. An even quicker way that you could go about that, though, is this factor right here of keeping in mind that this entire area under the curve has to equal 1. And so if I took 1 minus the amount of individuals proportion-wise that did worse than me, so if I did 1 minus 0.3707, I will get this exact same score of 0.6293. So those are two different ways that you can go about determining whether or not you can calculate this area above your test takers or below, is keeping in mind that the entire area has to equal 1. And so you can use these different components under the scores and under the curve to determine the other elements and proportion values here, knowing that they always have to equal that final value of 1. Not only can you use the z-scores in the standard normal table to help you find areas above you and below you, but you can also use it to figure out the areas between two certain scores as well. So let's say you wanted to figure out the proportion or percentage of test takers that scored between you, who again we're going to keep as a value of 1020, and your friend who scored a 1220. All you would have to do in this case is calculate each individual z-score, which I've already done for you here. So here's what it would look like if you scored a 1020, and here's what it would look like if you scored a 1220. And this will give you both of the areas to look up under the standard normal table. So again, once you get the z-score, your next step is to go look up these values on the standard normal table, keeping in mind that you'll always have to use the absolute value. So in this case, again, we're going to look up 0.33 because we're also rounding to the hundredths place, and we'll only ever be looking up values on the standard normal table that are positive. So that's why we take that absolute value. From both of these z-scores, we can look up the area B of each of these. And I've done that for you here just to save a little bit of time, but feel free to go ahead and practice this on your own as well. And I see that area B, which in this case is showing me, again, that 12.93% of test takers did better than me, but still below average. But then let's take into consideration the second z-score here in area, because my friend scored above average, and I know that for two reasons. One, simply their score was higher than average, right? 1220 is a higher score than 1083. But my z-score was also above average, meaning that I was a certain amount of standard deviations above the mean, and in this case, it was 0.706 standard deviations above the mean. And I know that because that was my calculated z-score right here. And so when I looked up that value on the standard normal table, I found that area B for our second score was 0.2611. So we can add both of these areas together to figure out what percent of test takers scored in between us. So I can take this area and sum them together, which is what I did here, to determine that 39.04% of test takers fell between score-wise myself and my friend. Another way to phrase that is that 39.04% of test takers scored between a 10-20 and a 12-20. And so again, this is what z-scores allow us to do, is standardize between units and figure out these percentages and percentiles fairly quickly. The last example we will work through here is looking at the area between two z-scores. So let's take an example again of our test taker score of 1020. So we're using that same calculation for our z-score, but this time we're using an individual that actually scored worse than us. In this case, our brother only scored a 920. And so what do we do about this area knowing that both of us scored worse than average? So we're only working on the negative end of this distribution. But we also have this area that overlaps, which is what I have designated here with these blue lines. In this case, what I'm going to point you to is this little tidbit down here, which says if both of your z-scores are positive, or in this case for us in this example, both are negative, we can subtract the smaller area from the larger area to get our total. So in this case, when I looked up that area B for our z-score 1, so this is the one we've been working with this whole time, of 0.1293, and then the corresponding one for this score was 0.313. I can take, knowing that my brother's area B was all of this here, right? This entire area, because this is where his red line is here. But I'm trying to solve for just B2 here. And I know my area is between this value here of 0.1293. All I have to do to solve for B2 is take the entirety of the area, which I know from my brother's is a value of 0.3133, and subtract that by my known area of 0.1293. So in this case, this area of B2 is a total proportion value of 0.184. What I can do in terms of the interpretation of this is say that the percentage or proportion of test takers that were between my score and my brother's score was 18.4% of test takers, or a proportion value of 0.184. Okay, so we have reached our summary slide for Chapter 5, and I know this was a lot of information, a lot of which was probably new too, so if you need to go back and watch this video again, feel free to do so. This is certainly one of those concepts I think that clicks a lot more the more that you do it. And so with that in mind, let's start from the beginning of this lecture and move towards the examples that we just finished up with. We started off with our conversation about what the normal distribution and normal curve were both hypothetically and theoretically, especially within construction in relation to our empirical rules. So the relationship between the two of these, knowing that within 1, 2, and 3 standard deviations of our average value, we would expect a corresponding amount of 68, 95, and 99% of our values to fall under that normal curve. We also talked about why the normal distribution and curve was important in social science, so be able to articulate that as well. Why are we even doing this in the first place? And lastly, we use the standard normal distribution to find both individual observations, which is what we did with our St. Louis Cardinals examples, and also areas under the curve, which we did with our SAT versus ACT examples as well. So again, overall from this lecture is this new idea of z-scores and standardizing those units, understanding that both conceptually and then in practice by calculating our z-scores, and finally, how can you interpret that within context? It's one thing to actually get a z-score and have that raw number, but what does that actually mean? What does that mean to yourself, to your reader, and within the broader concept of that problem and that context? So keep that in mind as you work through this. If you have any questions, feel free to reach out to me as always. I know this is tricky material, and so again, this is one that you might have to watch another time, but if you feel confident about it, then you should feel good going into the next video as well. If you have any questions, feel free to reach out. Otherwise, I will see you in our Chapter 6 video.